we have Filipe Correia, who will be presenting Pushing N times 400G Further. Filipe is a business development manager for Tier 1 service providers. He's been working with Ribbon and has traveled from Texas to join us. This is his second time presenting at NANOG. His first time was a talk from NANOG 78 in February 2020 about IP optical awareness and correlation for traffic optimization. Welcome back, Filipe. It's a pleasure to have you back with us today.
All right, I guess Texas is popular today. All right, what are we talking about? Pushing N by 400 gig further, right? Why am I talking about pushing N by 400 gig further? So at the end, forward here. So really at the end, I mean, at the end of the day, when we look at this, you've got the, obviously, capacity to demand is continuously increasing. You've got obviously different application drivers that are driving that, content, 5G infrastructures that are being built out. You've got continuous, automation, and of course, higher flows happening with machine learning capabilities, autonomous capabilities, AI. But there's also densification as well. That's a big part of it, right? So it's not just capacity want. It's also densification, higher density from a resource standpoint, right? Dropping down the amount of fibers, right? Fiber relief, less resource from a hardware point of view, right? Smaller data centers. So when we look at it, obviously from a data center standpoint, right? The data centers have been driving the market now for a long time when it comes to capacity and reach performance, maximizing that. Now, if we kind of look at where we are today, right? From a lane standpoint, right? Of client interfaces coming into that data center, you're looking at, traditionally it was about 100 gig. This is transitioning to now 400 gig. And honestly, 400 gig is becoming the de facto now, moving forward. So now we need to be able to transport multiples of these 400 gig lanes or interfaces, client interfaces. Right around the corner, there's 800 gig. So we're having to haul not only obviously these 100 gigs that are transitioning down to 400 gig interfaces, 800 gig is right around the corner that we're going to need to, of course, transport across the different data centers. So again, looking at it, as I'm saying here, what happens with the data center goes outside the data center. So it's a little bit opposite of Vegas. Okay, so what happens in Vegas stays in Vegas. That's not true at all. But when it comes to obviously data centers, all this information has got to get out as well. And so what we're looking at doing is how do we bundle all of those 400 gig lanes across these interfaces for higher performance distances. Okay, so today when we're talking about traditional data center interconnectivity, there's two camps or two trends that are predominant now, right? So you've got obviously IP over DWDM, which has become the predominant topic lately, of course, that's coming into play, more and more technology being invested into that. You also have IP over optical transport, which is traditional. There's been a little bit of an evolution that's happened there, of course, with regards to disaggregation of optical devices with dedication to these optical transponders or transceiver shelves. So if you look at IP over DWDM or a direct connect type of model or IP over OLS, traditionally you're looking at a low launch power, -10 to 0 dBm. That's changing. It's improving now. You're going to start to see potentially higher launch power transceivers integrated into the router as well. Now, for this session, I'm going to focus on IP over optical transponders or transport. So we're looking at a higher launch power of 0 to 3 dBm. So you're looking at obviously some transponders that are either proprietary type of transponders that are coming out to the market to provide that higher capacity, higher distance performances that are out there, that are needed. I'm not intending for this conversation to be a one versus the other one, right? They both have their pros and cons and values. One is simplified, one is a little bit, obviously a lower cost implementation with IP over DWDM, but then there's a value when it comes to obviously higher capacity, higher reach needs with IP over optical transport. So now, typically when we're talking about higher launch power transceivers, there's a couple of use cases predominantly that come into play. One use case is a capacity and reach optimized type of capabilities or transceivers. And then there's another, of course, use case with regards to cost and power optimization use cases. I'll touch on that one on the next slide. But with regards to capacity reach and performance optimized use cases, these are, as I was mentioning, these are the typical transceivers that are larger transceivers that are typically proprietary type of transceivers as well. They're typically embedded transceivers. They are now coming out in more of a pluggable version as well. These do provide newer capabilities or advantages in DSP to give you that higher transmit rate capabilities. And of course, there's proprietary capabilities or techniques that are leveraged by the different vendors to achieve that. Okay. So as mentioned, as I said, there are pluggable versions that are coming out, but what you're starting to see now in this space from a higher capacity, you're starting to see 1.2 terabit capabilities coming out with these transceivers. You've got around the corner next year, potentially 1.6 with the different types of DSP technology improvements there. When you look at the sweet spot with 800 gig, now you're starting to see distances into that regional type of distance space, right? 1,500 kilometers, 2,000, up to maybe 2,000 kilometers of achieving 800 gig. Now that's a big jump, right, from where we were before. And then with 400 gig, capabilities there of going ultra long haul. So these are distances across the country, right? Submarine type of distances, but with 400 gig now. So that's right now starting to happen into 23 and into 24, and then further capabilities, as I mentioned, in the DSP technology. Now, on that cost and power optimized, they're not focused on maximum performance, achieving that maximum performance. They're more focused on cost efficiency, power optimization, smaller form factors. They're standard multi-source, multi-vendor type of transceivers. So giving you obviously the capability of being able to standardize this across any type of vendor deployment, right? Small pluggables, but now giving you 400 gig capability with 0 dBm capabilities as well from a power point of view. So you've got performance that are getting closer to that regional distance, maybe hitting that 1K distance soon as well, but you're getting that capability. Now these are at a lower, performance standpoint based on standardization, right? The normalization of the capability, right? You don't have that proprietary technical advantages that are being put in. You're getting a standardization, typically driven by OpenZR, OpenZR+, OpenROADM, etc., defining that normalcy on the transceiver technology. Okay. So now, how do we engineer, obviously, these transceivers to provide that N by 400 gig capabilities there? It's at a high level. Let me be careful. At a high level, it's rather simple, right? There's really a few factors that come into play. So you've got modulation. Modulation is basically the amount of bits per symbol, which didn't dictate how many symbols are being leveraged, right? These are different sine waves. And obviously, this provides a level of density depending on how much modulation you're choosing. And you've got a baud rate. Baud rate is the transmit speed of those different symbols, or the receive speed of the different symbols. Okay? And then last but not least, right, you've got some fixed factors capabilities, and 2 polarizations to take advantage of. And you also have to be cognizant of your forward error correction overhead. Okay? So that's about a 50 to 20%, if not a little bit more than that, of overhead that you've got to account for. So if we look at this now, okay, let's take a look at these with regards to, depending on the different line rates that we're talking about, 400 gig or 800 gig or 1.2. If you look at the different modulations, I think we've hit our peak here with what you can do, right? It's not a, free lunch here. Everything has a cost. But I think here with modulation, with PCS or probability constellation shaping, I think we've hit that with regards to how many bits we can put in there with the amount of symbols relevant to distances, right? That's what we've got to keep in mind. The higher density that I put in with modulation, the less distance that I can travel without having a problems distinguishing the different symbols. Okay? Now, fixed, as I already mentioned, the polarizations, forward error correction capability, right? That's fixed, right? So what does that leave us with to play with? It's baud rate at the end of the day, right? This gives us an advantage. That's not physics limited, as modulation was, right? As those symbols are going down that fiber, that distinguishing, that's physics limited, not technology limited. But with baud rate, now we can take advantage of newer technology advancements in DSPs and being able to transmit these symbols faster, okay? So just kind of sticking to that modulation aspect of it, right? Just for those who haven't looked at this long enough, and it was rather new for me too, looking at it over the last few years, as I was just trying to understand capacity capabilities. My background was predominantly on the IP side, so if you're all optics, don't be mad at me, but it was predominantly on the IP side. But looking at this with modulation, you can quickly take a look with constellation, the different amount of symbols that you've got, right? So on the left-hand side, I've got QPSK or 4 QAM, which basically is 4 symbols, right? So over longer distances, right, the laser or the receiver can still distinguish those 4 symbols. Now you look over to the right, now that's only a 16 QAM, so 16 symbols, right? You can go to 64 QAM, but basically this starts to get denser, right? So as you're adding modulation, and depending on line characteristics, right, and as we know it, there are a lot of issues out there with different legacy implementations in the field, right? So depending on those line characteristics, you have limited distances in just trying to maximize that modulation and get the most out of it, right? So it gets a little bit denser, and as I mentioned, it's a difference in phase and amplitude for each of these symbols. So as you get further along, it's harder to distinguish the different symbols. So there's a well understood, right, or distances that you can achieve with these different modulation schemes. So I've got a quick little visualization for you of understanding the different distances, the typical distances, again, give and take, right, depending on the line characteristics of these different modulation schemes. So if you look at, again, as I mentioned, 64 QAM a little while ago, you're looking at, with 16 bits, 120 kilometers, right? You start going less, right? 5 bits starts to increase to 400 kilometers, so metro type of deployments. And then you get into these 4 bits or 16 QAM, metro to regional, 15 kilometers. That starts to become a nice sweet spot. And then all the way up to 4 QAM or QPSK, right? 2 bits, as I said, less dense, gives you that capability of looking at this or having the capability to receive this over ultra long haul distances, right? 5,000 kilometers. So typically what you're seeing, the gold standard or where everyone is gravitated towards from a ultra long haul or metro / regional, you're looking at QPSK, right? 2 bits and 16 QAM as traditionally what's being used more and more. So let's take those for now. And now kind of reverse engineer this a little bit with regards to baud rate, right? This is where we can really start taking advantage and seeing what we can do with those modulation schemes. So just looking at, again, for 400 gig or 800 gig, right? What can I do with those different modulation schemes? What baud rate do I need? And you saw the formula before, right? So now this is specific to baud rate here with regards to line rate, and obviously divided by your modulation, your 2 polarizations, and your overhead that you need for your forward error correction. So for 400 gig at 16 QAM, you're looking at 62.5 gigabaud, right? So 400 gig, but for ultra long haul, 125 gigabaud, okay? Gives you a quick little understanding of what you need still with that particular modulation scheme. 800 gig, 125 gigabaud for 16 QAM. And for just 4 symbols, so QPSK, you're looking at 250, greater than 250 gigabaud. Okay? So what are we seeing right now, right? Or right in the near future, right, as it's coming out? So traditionally over the last year or two, right, from top vendors, best of class DSPs that have been out there, you're seeing 7 nanometer DSPs, right, at 95 gigabaud. And that was giving you, for 800 gig max, it was giving you some metro distances. And for 400 gig, you had a level of good long haul, at least with 400 gig on that. So 95 gigabaud for 800 gig, that can determine your distances there in 400 gig. Now, right around the corner coming out, there's proof of concepts that are happening today that have been going on actually, you know, at least half of this year, if not in OFC, for those who, you know, attend OFC, you know, second quarter within this year. So you're seeing capabilities with now 5 nanometer DSPs that are leveraging 140 gigabaud. As I said, the sweet spot was at 800 gig. Now I'm seeing potential distances here of that metro regional, 1,500 kilometers, and then maybe eventually getting up to 2,000 kilometers. But now you can see that sweet spot of having what we've been calling a real 800 gig for longer distances, covering your metro and covering many of your regional application solutions. So as I said, right, next year, this is the immediate that I'm showing you right here. Next year, then you've got more further advancements on those DSPs. You've got 3 nanometer DSPs and the capabilities that are being put there in improving, obviously, gigabaud performance. Okay, that was my, capacity and reach optimized. Also with your cost and power optimized, there's been evolution here, of course, as well, right? You're getting smaller. You had a year or 2 years ago, CFP2s that were released, 400 gig, 64 gigabaud. That was a 7 nanometer DSPs being leveraged. Now you're going to smaller QCP-DD at 64 gigabaud, supporting 400 gig. And around the corner in 24, now I want to be careful. It's a little hard to condense it on the slide there. I show the beginning, but really from a standardization standpoint, a little further into 24, but around the corner already, because we're towards the end of 23 really, you're seeing 800 gigs, so further capacity with those QCP-DDs, right, at 120 gigabaud, right? So now you get better capacity, better performance with those transceivers. Okay. So what does this mean today, right? As I said, right, where are we in comparison to looking at these different transceivers being either A, capacity and of course performance optimized, or B, obviously power and cost optimized. So today, with regards to on the circle there on the left-hand side, right, the metro regional 16 QAM for 400 and 800 gig, you're already able to achieve those in 23 and 800 gig into 24 with those power cost optimized transceivers. With the newer proprietary transceivers coming out, right? So multiple vendors are releasing this technology, right? As we speak, you're looking at capabilities of supporting 400 gig at 100, greater than 125 gigabaud. That gives you that ultra long haul distances, 5,000 kilometer distances with 400 gig. That gives you also 800 gig support at 16 QAM, right? So 4 bits per symbol at 125 gigabaud, right? So 800 gig, that's going to be available already in 23, right? At the end of 23, you already have this capability there. With regards to 250 gigabaud, there's no roadmap yet, right? So it's not there yet, but you can imagine as things are progressing from a baud rate and the DSP technology, we'll probably get there at some point in the near future, right? So as I said, you've got newer technology from a 3 nanometer point of view coming into the picture already next year. Now, from here, so you can see the capabilities that are now there that allow you to obviously have that N by 400 gig lanes, right? So multiple 400 gig lanes for further distances, the ability to carry 800 gig to regional type of distances as well, right? So now higher capacity, further distances that are able to be supported today immediately. One more thing, if I can move. And apologies, people, I went really fast. So, all right. So one last thing, right, to kind of talk about, right, because everything comes at a cost, as I said. You know, modulation came at a cost. Yes, baud rate. Yes, that was technology, but that still came at a cost of improving that technology. But with regards to also another cost when it comes to baud rate, you've got to keep in mind spectral density or spacing, right? So what was going on before with 800 gig and 95 gigabaud that I was talking about earlier, right, which gave you 800 gig capabilities, but lower performance across that. You had a spacing of 112.5 gigahertz. A little odd, right, when you start looking at it, especially as you're trying to maximize packing of those wavelengths or those channels on a line. Okay, so it's a little bit of an odd number there, but now what we're looking at with newer technology coming out, now you're getting back to a normal type of spacing, 75/150 gigahertz. So if you look at the rates, as I'm showing you here, 120, or pardon me, 1.2, you know, the two channels, that's 2.4 terabit versus 800 gig, three channels, right, to give you 2.4. You're wasting some of that spacing, that spectrum spacing right there as well. So now we're able to efficiently pack this a little bit better on that line to maximize as many channels of those higher capacity rates on a single line. And so you're seeing a better rationalization of the spacing of these particular wavelength channels. Same thing on the power cost, the newer pluggables that are coming out, right? So with QSFP-DD, 64 gigabaud, 75 gigahertz. So for every channel, you're only leveraging 75, but as you go up to 120 gigabaud, now you're doubling that. So 150 gigahertz becomes that cost of the particular spacing, but still pretty consistent versus what we had before of 112.5. Okay? So everyone, I'm looking at the time, and that's the fastest I've ever been in a presentation. And there's about 7 minutes left, but I don't know if anyone has any questions there with regards to that. Yes.
First of all, thank you for the session. Myself, Manish Krishnan. I am from Google. I'm also part of the Nano HPC committee. So my question is, if you do a apple-to-apple comparison with 400 gig long-range optics, like ZR or ZR plus versus 400 gig normal optics, if we use this long-range optics without any kind of a transponders and non-ZR optics with transponders, if you want to send a 25.6 terabytes of traffic or 50 terabytes of traffic, do we have any numbers like how much we will save on cost and power if we compare ZR plus with non-ZR optics for similar number of traffic?
I don't have any numbers to share. It's a great question, right? That's the business case to look at. You're looking at it a little bit further to look at the advantage and the comparison below, right, with regards to it. But I will say this. Over the last couple years, pricing of 400 gig transponders has been dropping almost equivalent to 100 gig transponders, right, as we looked at it. Happy to discuss that with you, some of the pricing that we're working on, especially with the tier ones, right, as you're looking at scale and volume. But pricing, that's another big point to make, right, when we looked at, when we're talking 400, you notice I didn't have on there 300, 600, all right? Those didn't become really standards. It became 400 increments, right? Why? Not only because of the technology, but the pricing. Pricing drove it, and then there was a big factor of the IT modeling and planning for customers, but pricing drove the drive to go down there. But it'd be a great conversation to look at the comparison ZR Plus with gray optics to see the cost benefit between the two. I don't have any that I can share with you right now.
Yeah, thank you. And one more question I have is, when we go with this 50 gigs SerDes to 100 gigs SerDes, right? Do you have any kind of data about like how should we plan to build a network considering 50 gigs SerDes to 100 gigs SerDes for this high-end optics like 400 gig or 800 gig, do we see any kind of a latency improvement or power improvement in this SerDes to long high density optics comparison?
We do. Let me work with you offline, though. We could probably share some of that information to go with that.
Gordon Gidolfo from Think Fiber. Thank you very much for the presentation, Felipe. I was wondering about, you were presenting essentially improvements from the transceiver side.
That's right.
And I was wondering if you folks also have any info about improvements from the fiber side of things, like doped fiber, improving reach and achieving higher modulations in longer distances, if there have been any big milestones in the recent times.
I don't have actually any information on that. I'm sure there has been, right? When looking at the different fiber modes and capabilities and improvement in the manufacturing of those particular fibers, I'm sure there is. I personally don't have the information, but we can work with you to get that detail if you like. But I don't have it. I'm sure there is.
It's just a personal curiosity. Thank you very much.
No, you're welcome. Thank you. Is there another question that I cannot answer at the moment? Okay. Again, everyone, thank you. And I did good on time, though, apparently.